This is lesson 4.3, Patterns and Nonlinear Functions. Your objective is to identify and represent patterns that describe nonlinear functions. A nonlinear function is a graph whose graph is not a straight line or part of a straight line. Notice this graph is not a straight line, nor is it a part of a straight line. Just like linear functions, nonlinear functions can be represented using words, tables, equations, sets of ordered pairs, and graphs. A linear function is a function whose graph is a straight non-vertical line, or part of a non-vertical line. You can look at these examples. They're all straight lines and none of them are vertical. A nonlinear function is a function whose graph is not a straight line or part of a straight line. Notice all these graphs are not a straight line, hence why they're nonlinear functions. Classifying functions as linear or nonlinear. Problem 1. The area in square inches of a pizza is a function of its radius r in inches. The cost in dollars of the sauce for a pizza is a function of the weight in ounces of sauce used. Graph these functions shown by the tables below. Is each function linear or nonlinear? So our first table is the area as a function of the radius. Our area depends on the radius, so area is our dependent variable and goes on our y-axis, and I've used an interval of 50 since our numbers go from 12.57 all the way up to 314.16. Our radius is our independent variable, so that goes on our x-axis, and I've used an interval of 2. So let's plot our points. And let's figure out if this is a linear or non-linear function. So notice our points kind of curve upwards, so these are not on a straight line. So this function is a nonlinear function. As for our cost in terms of weight, since our cost depends on the weight of sauce used, the cost goes on the y-axis, and I've used an interval of 50 cents because our numbers vary from 80 cents all the way up to $4. The weight is our independent variable, so that goes on our x-axis, and again I've used an interval of 2's here. So let's figure out if this is going to be a linear or non-linear function. So if you look very carefully, it looks like our points all fall in a straight line. So this is a linear function. Representing patterns and nonlinear functions. So the table shows the total number of blocks in each figure as a function of the number of blocks on one edge. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So when we have one block on an edge, the total number of blocks in the figure is 1. When we have 2 blocks on one edge, there are a total number of 8 blocks in the figure. When we have 3 blocks on one edge, our figure has 27 blocks. So the ordered pairs will be our x and y, x representing the number of blocks on one edge and y being the total number of blocks in the figure. So we have 1, 1, 2, 8, and 3, 27. So in words, we need to figure out the pattern. Well, the total number of blocks, y, is the cube of the number of blocks on one edge. Notice if I take 1 and I cube it, I get 1. If I take 2 and I cube that number, I get 8. 3 cubed is 27. So our equation is y is equal to x cubed. So now let's graph these numbers. And actually, before we graph, let's figure out the rest of these. So 4 cubed would be 64. And 5 cubed would be 125. So our ordered pair here would be 4, 64. And our ordered pair here would be 5, 125. So our number of blocks will go on the x-axis, since that is our independent variable, on an edge. And our y-axis will be the total number of blocks, since that is dependent on the number of blocks on an edge. So now we need to figure out our intervals, and we can say for the number of blocks on one edge is 1, 2, 3, 4, and 5. Since our total number of blocks varies from 1 through 125, we will need to use a larger interval. Let's use 20s. We can go by 20s. And then we can plot our points. So when we have one block in the figure. When we have 2, we have 8 blocks in the figure. When we have 3, we have 27 blocks in the figure. 4 gives us 64. And 5 gives us 125. So this is a nonlinear function because all the points do not create a straight line. A function can be thought of as a rule that you apply to the input in order to get the output. You can describe a nonlinear function with words or with an equation, just as you did with linear functions. In problem 3, the ordered pairs 1, 2, 2, 4, 3, 8, 4, 16, 5, 32 represent a function. What is a rule that represents the function? First, you need to make a table to organize your x and y values. For each row, identify rules that produce the given y value when you substitute the x value. Then you look for a pattern in the y values. So here we put our x and y values into a table, and we need to look at the first row. How do I go from 1 to 2? What rule will give me 2 if I use an x value of 1? So some rules that we could use is y equals 2x. So if I do 2 times 1, I would get 2. X plus 1. So if I do 1 plus 1, I would get 2. And y equals 2 to the x power also works because when I substitute 1 for the x, 2 to the first power will give me 2. So think of a couple of rules for your first row. Then you want to narrow down your choices. So we will eliminate some of the rules that we've chosen. So when we look at 2 and 4, y equals x plus 1 doesn't work for this ordered pair, because when I plug in 2 for my x, my y value should be 3, but I need to get a 4, so we can cross that one out. That one does not work. Okay, we'll eliminate that. Y equals 2 times x works for us, because when I substitute 2 for the x, 2 times 2 is 4, so that works. But that doesn't work for the next one, 3, 8, because if I substitute 3 for x, 3 times 2 is 6, so that does not work for the next ordered pair. However, this one, y equals 2 to the x power, works for all three. Well, let's just make sure it also works for 4, 16. If I plug in 4 for the x, 2 to the 4th power is equal to 16. And if I substitute 5 for x, 2 to the 5th power does equal 32. So it works for all the ordered pairs. What is a rule for the function represented by the ordered pairs 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25? So remember, first we need to create our table of x and y values. Okay, so we'll do our x values here, y values here. We have 1, 1, 2, 4, 3, 9, 4, 16, and we have 5, 25. Alright, so first we need to think about what rules will work for our first ordered pair. So we can do y equals x. That works, because if x is 1, then y equals 1. We could do y equals x squared, because 1 to the 2nd power will also give me 1. We can also do y equals (1) to the x power, because 1 to the 1st power will also give me 1. Now let's see if any of these work for the second one, 2 and 4. So if I plug in 2 for x here, that should give me 2 according to this, so that is definitely gone. If I plug in 2 for x here, 2 to the 2nd power does give me 4, so that works for that one. Let's just try our last equation. If I plug in 2 up here, well, 1 to the 2nd power is just 1 again, so that's definitely out. So far this seems to work. Let's try it for our next couple ordered pairs. If I substitute 3, well, 3 to the 2nd power does give me 9, and 4 to the 2nd power is 16, and 5 to the 2nd power is 25. So our rule for this one is y equals x to the 2nd power.